welcome everyone. So just as a reminder, Monday and Friday seminars are going to be here, and the group meetings are going to be in Bloomberg. So we're happy to have Joaquin, who's going to tell us about the Euclidean path integral in supergravity.
Well, yeah, thank you very much for the invitation. I'm very happy to be here. Yeah, I'm going to talk about these two papers with Matt, Luca, and Andy from last year, and this one that we wrote a month ago or so with Luca and Murat Kologlu and myself. Okay, so let me begin with some motivations of what I want to talk about. So in developments in the recent years, the Euclidean path integral played the central role to understand the unitarity of black hole spectrum and the dynamics, particularly with non-perturbative corrections like wormholes and things like that. So at least to me, that's a good enough motivation to try to understand it better. In particular, instead of looking at those type of corrections, I will begin by looking at more fine-grained information about the black hole spectrum near extremality that one can access through these kind of calculations, including some quantum effects, and ask questions like what is the degeneracy of the extremal states, what is the gap above them, etc. And last year I gave a talk in Princeton where I gave several examples. So this time I will focus on one, which is the 4D black hole, charged black hole in flat space. And Matt also gave a talk about it last year. So I will try to give a little different perspective in the first part of the talk, hopefully. And then I will talk about this argument. In particular, something I want to focus in, and that's why I want to talk about supergravity in particular, is how to compute supersymmetric quantities like an index of such things using the gravitational path integral that has some interesting things about them. Okay, so yes, as I said, I'm going to focus on 4D, n equals to supergravity in flat space. Let me know if it's too small or something for the people here. The model I will study is maybe not UV complete in the sense that one can embed it maybe in some examples in string theory, but I will focus on the pure gravity part, possibly coupled to matter, but hopefully the discussion is general enough that one can apply it to other models. But okay, for this gravity part of the spectrum, one has, well, of course, a metric. One has a gravitino, which, okay, it can be represented in different ways. One can take a complex gravitino and graviphoton, or the electromagnetic field that is part of the supermultiplet. And just to remind you, so the action is, I will write the more important part. This is for what I say later. Is Einstein-Hilbert with Maxwell term, and then, well, kinetic term for the gravitino. And then there are interactions between these fields fixed by supersymmetry, and then possibly plus matter. Yeah, so this theory has a local supersymmetry, and that one can write it this way. Well, I will just write roughly. This gamma for matrices plus other terms. So this theory has as solutions the Rice and Nordstrom black holes. Parameterized by mass and a charge. for Kerr-Newman, if we add angular momentum. And I will assume that these examples are familiar for most people, so I won't write down the metric of the Kerr-Newman one, but I have it here if I can write it, I guess. But we will write it in terms of the mass, the charge, and a parameter A that is related to the angular momentum of the solution. So what we want is to do a path integral and see what is the spectrum of this black hole. Okay, so first of all, let me describe a little bit more in detail because it will be important later, the boundary conditions. So we want to have some solution that looks like this, with some asymptotically flat space and some, well, black hole, and we will do it in Euclidean space. And the boundary condition on the metric is, well, straightforward, but just introduce some notation. So we want the metric to go to flat space, where this is Euclidean time, the radial direction, and this is the angles, and corrections to decay as 1 over r. And it will be important for later to fix, okay, for the electromagnetic field, we're going to fix the charge, either electric or magnetic. And that will be the simplest case. It will also be useful to fix the angular velocity and try to do it in a grand canonical ensemble where we fix temperature and angular velocity. And the way that appears here is in the following identification. Well, there are different ways to write it, but this is the one that will be more useful for what we want to see later. So phi has a period 2π, it's just the coordinate in the sphere. And fields have to be periodic or anti-periodic with respect to this identification. And the interpretation is that this is the circle that is becoming contractible at the Euclidean horizon. For the metric to be nice in Euclidean signature, we will take this to be real. So that's sort of some analytic continuation there. And yeah, this defines the angular velocity in the boundary conditions. It's something useful to think about. So for bosonic fields, this is just fields should have to be periodic under that identification. But for fermionic fields, it's a little bit more tricky, and it will be important for later. So I will, maybe it's too many details, but it will be useful for later. So imagine when one has some fermionic field psi. I will only write these two coordinates. So any fermionic field has to be anti-periodic around this circle that becomes contractible in the black hole metric. And it's useful to think of it also as a non-trivial periodicity around time circle alone, without shifting this angle too. And that can be done by, well, we can write it this way. So along the time circle, even if it's not the one that's becoming contractible in the black hole, we can define fermions or bosons too to have this periodicity with this minus for fermions and this factor for any field where J is the generator of rotations along phi. Okay, and one picture for this that is useful to have in mind is that if this is phi and this is Euclidean time, then, well, things are periodic or anti-periodic with respect to phi because that one is always contractible. The circle that is becoming contractible at the horizon is tilted in some way compared to Euclidean time by a distance I beta omega. okay, and it will be important later that the physical thing is this exponential and not omega itself when we look at all the saddles consistent with these boundary conditions. Is there any questions so far? Okay, so the idea is that we want to do the, as I said, the gravitational path integral over fields. And we want to ask to what extent this looks like a trace over the sector of fixed charge, because we fix the charge over some Hilbert space of something like this. Oh, I don't know if people there can see, but well, this is where the trace of e to the minus beta h plus omega j, where omega is the angular velocity. Okay, so well, as I said, one contribution is the Kerr-Newman black hole, where well, it's usually written, or it's more easily written in terms of m, q, and a. But for this ensemble, we want to write it as a function of beta, well, also q and omega. But the point that I was trying to make before with that, writing the boundary conditions in that way, is that there is a family of black holes that all satisfy the same boundary condition that are related by this shift. Where n is an integer. So these are different black holes. One had to sum over them, and the necessity to sum over them is related to the fact that spin is half integer. So if one doesn't sum over all these saddles, they're a little funny because they can be complex in Euclidean signature. So I'm not going to worry about that in this talk, but it was something that's interesting to understand better. But if one doesn't include them, one can get to contradictions similar to one mentioned in a paper from last week by Carlo and Oguri, where one can make black holes with average angular momentum to be any number, but where fluctuations in the angular momentum can be arbitrarily small. And that is inconsistent. But okay, the solution to solve that is to sum over all these saddles, and then the angular momentum is automatically quantized. Okay, so
so your boundary condition is real, but some of the saddles are complex.
Yes.
If I can read, you choose a mega imaginary, so there can exist a real saddle, but to get physically sensible answers, you include non-real saddles.
Yes. Yeah, even regardless of yeah, so you can look at this identification and also, well, including back reaction, when you look at the black hole, then you can compute the position of the horizon for these boundary conditions, and sometimes that can be complex, which means that you have to go along some complex direction to make it smooth. But yes, in terms of the boundary conditions, this is real, at least, yeah, real Euclidean method.
Let's say if you make omega imaginary, then everything is real, right?
Yes. So I'm taking this to be imaginary, but then you have to put it in the formula for, let's say, R plus in the Kerr-Newman method. And that's not always real. So that's the, so if you're far away, it's probably not the problem, but if you go where, so I don't know, I mean, it's an interesting question whether they should be included or not, and if you don't include them, there is a problem. So is that some motivation to include them? Is there any other question?
Are they safe in Lorentzian signature, or?
No, I think there will be complex. Yeah, like here, for them to be okay in Lorentzian signature, you need to take omega to be real, but I'm taking omega such that that thing is real, that appears in it. Thanks. Okay, so when we include this family of solutions, we have that the Euclidean prediction for the partition function will be a sum over this integer And we will work at large Q. I didn't say it, but I'm fixing G Newton to be 1. So we take large Q, so the black hole is big, and there is some semi-classical approximation. So we have some one loop term, and then we have the e to the minus the Euclidean action on these Kernigan black holes as a function of beta, omega, Q, and also n, because we have to shift. And just to give you some intuition about how they behave, I will write down the action as a function of n. I will write it, well, this is a complicated formula in general, but I will write the near extremality for fixed Q and low temperature, where this formula becomes a little simpler. And maybe more familiar. So so okay, I'm writing, it's just convenient to write this formula, to write it in terms of this parameter alpha instead of angular velocity. And this is just to make the periodicity in omega. Instead of looking at the periodicity in omega, it's just easier to look at it in terms of alpha, where it's just defined because it has period 1. So just for that reason. And then the action has this form. So if one is in principle away from extremality, take for example alpha equals 0 to compute the partition function with 0 angular velocity. Then clearly all saddles with n bigger than 0 or n different from 0 are going to be subleading in this sum, so one can in principle forget about them in most cases. But when one goes close to extremality, this correction that depends on n is proportional to temperature, and then all these saddles have approximately the same action, and one has to include them to get sensible answers. Yeah, so before I move on, something that would be useful to have for later is the mass for these cells. What is the mass of the here as a function of temperature, angular momentum, and central charge? This is again near extremality. So this is for temperatures smaller than 1/2, and then the momentum smaller than Q². Okay, the interpretation of this formula is that we have some extremal mass, which is the mass at 0 temperature, which is Q plus J²/2Q². So this is the extremal Reiser-Nordstrom mass. And this J² correction comes from rotation. And again, there's a complicated formula that for small enough J's has this form. And the mass above extremality depends with temperature squared with this prefactor. And for those of you familiar with JT gravity and all that, this is the correction that comes from the fact that there is an ADS2 throat and there is a JT mode there. That gives energy that goes as temperature squared. One can also, well, if one has an SU2 gauge field, one can also reproduce this dependence with alpha, which is like a chemical potential for that SU2 gauge field from rotations along S2. And from that gauge field, something else that one can reproduce is the fact that one has this J² correction to the extremality, mass. Okay, so that's what so yeah, the geometry for these black holes looks like there is a long throat with an ADS2. Process two throat, and that's what controlling this behavior. Okay. So as I said, near extremality, the sum over n is not that innocent, and one has to be careful about how to do it. But in order to do it, it's also important to know how the one loop determinant depends with n. So that's something that is a little harder to compute. And that is the topic, or at least we give an argument in the paper with Matt, Luca, and Wenli of what the answer should be at low temperatures. So let me write out the formula. So the details are not super important, but I just wanted to show that there is a formula. So there are a couple of interesting features about this. And this is, in a sense, we give some arguments, but it's a proposal that would be nice to check directly in 4D. And the way we argue for it is using the fact that we have this ADS2 throw in this limit. And this has two parts. So one part is there is a term that is temperature independent and comes with the charge to some power. And this is what people have been computing mostly before in the past with things like the quantum entropy function of Sen and that type of calculations. And this basically comes from the fact that in this throat we get a JT mode from gravity, and then we have like a tower of free fields, or from the KK modes when one does the reduction under some assumptions. Other than gravity or gauge fields in 2D, everything else gives contributions that is temperature independent. And that's something that in Matt's talk from last year, it was more about like doing this reduction more carefully. But this contribution is important because it can be matched if this is embedded in some string theory example to log area corrections, because Q is proportional to the area, or well, the area is Q squared. But the part that is usually not ignored is regarding this JT mode, which is this, which gives you the dependence with the temperature near extremality, and also how it depends on these saddles and on the angular velocity and all that. Yes. This result has three contributions. One is from the JT mode, but as I said, I'm working with n equals 2 supergravity. So we also have fermionic modes coming from the gravitino in the throat. That's again something that was explained last year in Matt's talk. Basically, what's controlling the theory here is a n equals 4 version of JT gravity, which controls an immersion but broken PSU 112. Which is, so I'm not going to go through the details, but basically this has inside an SO2R, which is the broken conformal symmetry of ADS2, and SU2 from rotations along the sphere, and the fermionic. So to finish this review, or like this summary of the first paper, so let me tell you how the spectrum looks like once you include these one loop corrections. And well, there are some interesting features. First of all, when one looks at the spectrum as a function of angular momentum by doing a inverse Laplace transform, like to extract the spectrum of angular momentum from that formula, one finds that it comes in groups, or there is a certain combination of angular momenta that come always together. that comes in this form. And this is basically the spectrum of angular momentum in the super multiplet of the supersymmetry that is preserved in the throat. So it's easier to write the density of states as a function of not of states of some angular momentum, but of super multiplets. So they all come in this group. And maybe I will write it bold J or maybe J hat. Yeah. Okay. So and the density of states that one extracts from that formula it looks very simple in terms of this quantity as a function of m minus q, let's see. So one finds a delta function. So this is the only state that doesn't fall in this characterization because it's supersymmetric and it comes by itself with angular momentum 0, energy 0, or sorry.
I cannot quite read that.
Sorry.
It's a bit hard to read that color.
Oh, I see. Sorry. Thanks. Yes. Yeah, so here I wrote, it's not. Yeah, so here what I'm saying is that in the density of states, there is a term that is a delta function of energy, where energy is measured above extremality at 0 angular momentum. It has 0 angular momentum and it's multiplied by a factor of e to the s naught, where s naught is big Q squared. And this is the extremal area. So these are the BPS states, which have a large degeneracy of order e to the area. And then there is a density of other super multiplets, which comes in a continuum. And they all have a gap. And so, for example, this is the multiplet one with highest spin 1/2. This is the one with highest spin 1, etc. And they all have a gap as a function of j hat that goes as j hat square over 2q. Yes. So yeah. So the interpretation of this, when we look at states of angular momentum different from 0, is that it's reproducing this j square over 2q cubed there that one finds from the near-extremal analysis classically. And if we look at, for example, well, just to give you an idea of how it looks like, the density of states not of the super multiplets, but of states of fixed angular momentum instead. The most interesting, or well, the one that is connected to the supersymmetric states is the one with angular momentum 0. And in that case, the density of states looks like well, the delta function from those states, and then it has a continuum, and it has a little kink here where, so here we have a supersymmetric states, then we have a gap until the super multiplet with j equals 1/2, because it has a j equals 0 component, and this is 1/8 cubed. And then we have a little jump here where the super multiplet with j hat equals 1 starts contributing for states with 0 angular momentum. And then it goes to a continuum. And something important is that, so there is a formula for these curves that I'm not going to write down because it will take me a little long, but important features are that this is a square root edge. And at large energies, this goes as e to the something square root e, which matches with the semi-classical area from the from the classical evaluation of the action. So this is the Bekenstein-Hawking area term. But an important feature is this gap, which in examples in string theory is observed. They have a very stringy explanation, but it's, I don't know, I found it very interesting that one can reproduce it from just gravity with these simple quantum effects. And then this delta function corresponds to the states that are counted by indices or things like that that are protected under supersymmetry. So last comment, so this scale, this gap scale, 1 over q cubed was identified in a paper by Preskin et al. In 91, I think, as one can identify it as a scale in which the statistical mechanical description of the black hole has to break down from, and the argument comes from thermodynamic reasons. Basically, if you have a system where the entropy, or well, the energy goes as t squared, then when t is of order 1, when the energy above extremality is of the same order as the temperature, there is expected to be some large back reaction, and one can see that explicitly by computing this one loop correction.
The modern perspective is just simply that the quantum effects of this Schwarzian mode become important, and you take them into account, and you still have a statistical mechanical interpretation,
yes,
which is what you are discussing.
Yes, yeah, that would be the, or yeah, so that's the modern interpretation, and besides the interpretation, there is also like something analytic one can do and see how.
Yeah, it's a resolution of that problem. I mean, they had some problem, and this is the solution to this problem.
Well, I think in their paper they also mentioned that there is some kind of flashback reaction, because when they emit one Hawking quanta and the energy above extremality is of order of the temperature, then that will produce the horizon to move.
Right. So those are all words, but,
yeah,
but at the end of the day, there is a calculation that solves all these problems, right?
Yeah. So if someone would have computed the temperature dependence of the one loop correction, they would have noticed this, but that wasn't computed. Yeah. And
in that sense, it's a situation where this effect of back reaction, which at the time looked very complicated, completely solved.
Yeah, that's a way to say it.
So the calculation that you did is just it's all in 4 dimensions.
Well, we give an argument that this is a good approximation of the 4D result. And some people disagree, but there is no other calculation. So it would be nice if someone like just do the calculation in 4D, but it's difficult to do. But yeah, we give an argument. We try to explain in as much detail as we can why this the 2D calculation in this ADS2 is actually a good approximation of the 4D problem.
But in principle, one could do it in 4 dimensions. And
it's just difficult. It's just technically difficult to compute the. One case in which we can check this formula is in 3D, where one can do the one loop calculation using. Well, one can either use the trick of Maloney and Witten, or use the heat kernel like in the brute force way, and find the one loop determinant, and one can check that it gives this exactly. So that's, I don't know, at least one data point where one can compare it with something, get the same answer. But yeah, in higher dimensions, I mean, people compute one loop corrections around black holes, but they always focused on this contribution. That is not the interesting one to look at the. So yeah, these contributions kind of maybe just renormalize what you mean by the extremal area with these log A corrections, which are nice to compare with string theory, but they don't tell you about the shape of the spectrum near extremality. So that's the. Yes, yeah. So this can be seen as a resolution of this problem, but having supergravity is important. And in this talk, I focus on supergravity, but there is also a different story for gravity. Instead of going there, what I can do is to look at the spectrum of near-extremal black holes that are not BPS. For example, when they have some non-zero angular momentum. So they kind of behave the same as in Einstein-Maxwell theory, and then the density of states just goes something like this. So here there are 2 jumps, which is just the different points where the different multiplets that have a certain angular momentum can contribute. There is a continuum that goes to E to the area, but then it goes to the extremal. So this would be the extremal k squared over 2q cube correction above q. So well, the total mass will be q plus this. And the density of states, instead of going to a large degeneracy, goes all the way to 0, and there is no gap. So this feature that was observed in string theory of a large degeneracy, a gap, and then a continuum is not true for non-supersymmetric states. So that's something where having an analytic control at least tells you in more detail how different systems behave. While I think in the 90s, the expectation was that this would be the spectrum for any near-extremal black holes, maybe, I don't know, but it doesn't seem to be the case. Okay, so now I will move on to computing the index. We'll play how to compute the index using supergravity. I will call it the gravitational index, just because, as I said, we are not going to commit to any UV complete model. So in principle, well, the meaning will be more clear in a UV complete model, but we can still do the calculation in gravity and see what it gives. And yeah, so by index, what I mean is the trace over these fixed charge states of -1 to the f e to the minus beta h. So we want to do a path integral in gravity that it will give something that behaves as this quantity in field theory, quantum mechanics. And we would like to compute it at any temperature. And again, get a result that is consistent with how we expect it to behave. And yeah, so this is something from the second paper with Luca Murat. Okay, so before I say the way we do it, let me mention some like misleading approaches. So there is a -1 to the f. So the first thought is that fermions are periodic. So a way to compute it at finite temperature would be to take forget about angular momentum for now, take a near-extremal or a charged black hole at finite temperature and just force the fermions to be periodic. And we can force fermions to be periodic. And of course, this is wrong for two reasons. First, the contractible circle is time, so it would be inconsistent, or it would be singular in the horizon to ask the fermions to be periodic, so that cannot be done. And another problem is that if you actually compute the path integral, basically the fermions are irrelevant if you forget about that singularity, and you get an answer that is not consistent with this being controlled by only supersymmetric states. So this should, yeah. Maybe I should say that by that what I mean is that we should do a calculation where we get some number times e to the minus beta q. This is what for me would be a consistent result, where this number is the temperature independent, and it would be the number of bosonic minus fermionic states. So if we take a near-extremal black hole, we are not going to get a temperature dependence of this form. Okay, so the second option, that it's also incomplete, would be to realize that only states at 0 temperature contribute, only extremal black holes, we expect them to contribute. So we can take the extremal metric, which looks like this, and has the horizon at infinity. So we can compactify it and say that time by hand, say that time is periodic with period beta. And we can make fermions periodic because there is no horizon, it went to infinity. And this in principle is okay. And this was considered in a paper by Horowitz and Ross in the 90s. And this is a perfectly fine contribution, but the problem is that if one does the calculation of the contribution, one gets only minus e to the minus beta q. And this doesn't have the e to the q squared that one expects to count the number of supersymmetric states to be exponential in the area. So it predicts an entropy to leading order 0. But in principle, it's fine. It's just something one has to have. But it's not the one that is going to count
It might be an ill-defined path integral because of the fact that the tube is shrinking on the left.
Yeah, so in the paper, we argue using these 2D reductions that this should actually be 0. I don't know if that's related to this problem. So when we look at one of the terminals around it, there is something funny with the firm. I don't remember right now exactly, but there's something funny with the fermions that even makes it 0. So I don't know, maybe that's.
Well, I didn't have any technical arguments in mind, but I thought it might be ill-defined because of the non-compactness and not very nice behavior off of the left.
Mm-hmm. Yeah. Yeah, okay. Yeah, so maybe it's not. Yeah. But okay, one can also compute it and well, that we give zeros. Yeah, maybe it's. Okay, so okay, but even if it will contribute for whatever reason, it doesn't give the expected answer. So that'll be the whole story. So the way we do it in that paper is by well, first one can realize that -1 to the f is equal to e to the 2 pi ij. So so states with half integer angular momentum have -1 to the f -1 was only 1 plus 1, and we can think of this insertion of the -1 to the f as an inserting this operator, and then we can think of this as the path integral evaluated at the particular value of angular velocity, which is imaginary. So what this predicts is that the index would be the, say, gravitational path integral with inverse temperature beta and some omega given by 2 pi I. And this calculation we can do at finite temperature, so it's not going to have the problem of the horizon going back to infinity. And we can show that it's also supersymmetric and has gives an answer that is consistent with the properties we expect an index to have. So first let me mention how it solves this puzzle with the fermion mean, whether it's periodic or anti-periodic. So if you remember that square that I drew before, where this is phi and this is time, I was drawing the contractible circle to be some principle tilted in this direction. But when we pick this particular value of the angular velocity, the contractible circle becomes this. So the fermion has to be anti-periodic with respect to this circle, and also with respect to this circle, because this is just the spatial angle. But what this means is that fermions, because it's anti-periodic between these two, fermions are, well, +1, I mean, that is periodic along the Euclidean time. So this solves that problem of allowing for periodic fermions with a horizon at a finite distance in a smooth way. An observation that I'm not going to go into too much detail, but here I pick the particular axis in which the angular momentum points, and I look at rotations around that axis. But when one picks this value of angular velocity, one gets the same answer for any axis. So this recovers the rotational symmetry. The way to see it is that this operator is -1 to the f regardless of what is the axis of rotation. And the same here. So I can state the boundary conditions independent of the axis, but by just saying that it's periodic in time. Okay, so now we can compute the classical action of these saddles. Well, again, I didn't write down the metric, but it's Kerr-Newman. I assume people, or I guess you know where to look for it, or you have an idea what it is. But what I will write now is the action when we take Kerr-Newman with this particular value formula and see what it gives. And when omega is 2 pi over beta, we get exactly minus beta cube plus 5q squared. Or in other words, we get a prediction. Sorry, this. Well, that I is the index. This is action. This is minus the action. Newman. So the prediction for the index is this t minus beta cube 5q squared. So, okay, so now we get something that takes into account the mass of the extremal states and also what we expect to be the large degeneracy. Although the good thing about this approach is that in principle doesn't assume that the degeneracy is the same as the index, because there are minus number of Fermionic states. In principle, we could get different answers, but here I want to get the same because I know that all the supersymmetric states have zero angular momentum, so they are all bosonic. So in this case, we expect it to be true, but and it is. So this saddle contributes in this way. But there is an issue. Well, okay, before I mention the issue, another thing with this saddle is that we can compute the mass, and it's equal to Q. So this implies that the Killing spinor equation is integrable, and there is a solution. There is a Killing spinor. So this saddle is supersymmetric even at finite temperature. And also, well, which was discussed before, the Euclidean solution is completely real, at least for 1/4 pi q. Yes, temperature is bigger than 1/4 pi q. I think R plus becomes complex, but at least for this range of energy, the Euclidean metric is real. Okay, so. Oh, there are. Yeah, so the issue I was referring to before is that in the beginning of the talk, I argued that we should sum over complex solutions where we shift the angular momentum. Otherwise, we get answers that are contradictory with angular momentum being quantized. So in principle, we have to do the same here. The gravitational prediction of what the index would be a sum over n. But okay, of the one loop corrections and into the minus the Euclidean action, but the Euclidean action now for other saddles. Well, let me just write it directly. This is P2. So we get the term we want, but then we also have and this I'm writing in near extremality at low temperatures just to write an explicit formula. So if n, this n is so these are saddles where the angular velocity the angular velocity is the I beta omega corresponding to the index plus 4 pi m. So they are the ones I mentioned before. And if we look at this term for any n that is different from 0, yes, for any n that is different from 0, then this term will depend non-trivially with temperature. And then that's not the behavior we expect an index to have. Because here we already captured the energy of the states and the degeneracy. So there should be something that picks the n equals 0 as the only one. Should contribute. And well, the related problem is that if you compute the mass of these black holes for when n is different from 0, they also are not equal to Q. So they're also not supersymmetric, they don't have killing spinors. And that is actually what resolves the problem. Of course, we can see it from the equation of the one loop determinant I wrote before explicitly, but I don't want to do that. I just kind of want to give an argument that doesn't rely on too many details. And well, the argument is quite simple, like just that whenever you have a solution that is not supersymmetric, then the answer is 0 because of fermion zero modes. So when n is different from 0, then this is 0. And one can see that when n is equal to 0, this is some constant times this factor of q to some power that I wrote before. Only the supersymmetric solution contributes. Is there any questions? Okay, so this justifies why the final answer is given only by this term that I wrote here. Okay, so next I want to mention, probably very briefly, but so I didn't write down the killing spinors of this metric, and you can, but instead the only thing I want to do is to mention some work in progress where mention that these metrics can be rewritten in a different way, where I still will write the killing spinor, but it is known that they have killing spinors and they are written in the literature. So this is work in progress with Jan Boruch, grad student at Stanford, and Luca. And these are called Israel-Wilson metrics, but so let me write. So they have this form. So this is a different parameterization of 4D where I take Euclidean time and x1, x2, and x3. B and B tilde are two functions of only x. And they are harmonic. So they, box B and box B tilde is 0, where these are derivative with respect to x1, 2, 3. Omega is a vector that is a solution of this equation. So one has to solve this equation and put omega there, and that gives you. So this metric with this equation for omega plus a formula for. Well, I'm not going to write it down, but there is some formula for the field strength of the electromagnetic field in terms of B and B tilde. So this is a solution of Maxwell-Einstein for any function of B of x that nabla square is 0. And in particular, so the observation is that when we take V to be 1 plus Q. So when we take V and V tilde to have this form, where I wrote it this way to compare A with Kerr-Newman one, but it makes take this to be real. So what this corresponds to is like taking omega to be imaginary Kerr-Newman. Then this metric with this choice of V and V tilde, it's exactly the supersymmetric Kerr-Newman solution that I mentioned before. So, and the reason why I want to write it this way is that there is a paper by Todd from the 80s that shows that all metrics of this form, besides being solutions, they also have Killing spinors. So, yeah. And here the interpretation is that if one has the 3D x1, x2, and x3 spatial state space, one has, for example, this center at IA direction n. So let's call this direction n hat. Then this is to IA, which is real because I want Euclidean metric to be real. Then the separation and the orientation of these 2 points is determines the angular momentum of Kerr-Newman. Moreover, these solutions are allowed to be at finite temperature, so I can identify T with T plus beta. And the smoothness in the axis between the 2 points gives you the same function of A as a function of beta or of the angular momentum as a function of beta, the absolute value, as what one gets from Kerr-Newman. So, well, that's another way to see it from these metrics. Yeah, so that's an indirect argument that these are supersymmetric. Let me see. Okay, I guess I'm out of time, but I will make a couple more comments. That's okay. That's it. Okay. Well, the first comment that I wanted to make was that there is a generalization of these metrics that we are studying in that work in progress, where one replaces this by a sum, right? So this is still a solution, so it's like a multi-center version of the index calculation, where one can sum over, well, they can have different Qs and at different positions, with some constraints that come both from having the correct boundary condition at infinity and also being smooth everywhere. And in principle, those should contribute to the index, and it's interesting to see how they do. And they are similar to the ones that they are like rotating supersymmetric versions of the multi-center extremal riser norm that appear in some discussions of ADS2 as well. Okay. That's one comment. Well, another comment I wanted to make is that this procedure of computing the index by looking at the bulk solutions with imaginary chemical potentials appear in a lot of examples. I mentioned 4D charged black holes. Another example is ADS3, where one has to give imaginary chemical potential for, well, if one considers 4,4 supergravity in ADS3, one has an SU2 gauge field. One can give some imaginary chemical potential to that and compute the elliptic genus in that case. Another example is ADS5, that also people have been doing imaginary chemical potentials and finding supersymmetric solutions. And maybe we did this case because we thought it would be the more familiar example or simpler one can study this in detail. Yeah, there are some open questions, at least to me, that from the point of view of gravity, of why do these solutions have these nice properties of the index? that's one, like how to know that is there a result that whenever we pick this particular chemical potential that are supersymmetric, the action will be exactly of this with this temperature dependence. Because here we checked it explicitly, but it didn't have to be that way. They could have another temperature dependence. Another question is, from the point of view of string theory, we also know that this index is supposed to be independent of the coupling, and the coupling is sort of, well, is represented by higher derivative corrections. So it would be interesting to see if we add terms like supersymmetric versions of R squared or things like that, then whether this index will be independent of those. That would be interesting if there is an argument maybe from just gravity. And then the last two comments. Well, one comment is another question.
Shouldn't it depend on those couplings? Because there's this whole discussion of Buff and Strominger where you consider these other couplings and various.
Well, okay, I have to think about it. Yeah, I guess I was thinking of ADS5 where they would be, that alpha prime would be like related to lambda. That's like the coupling.
In that case, perhaps you don't expect. Yeah, but yeah, so there might be some couplings that do change the value.
Okay.
I mean, there are black holes for which their actual value of the entropy is different than the value in gravity. So
yeah, well, there could also be cases where the saddle that computes the partition function, the entropy is not the same one as the index. I don't know. I guess that's another possibility also. But yeah, I think you're talking about something else. Yeah, sorry. I guess when I said that, I was thinking about the ADS5 example. Okay. Well, okay. Well, one can add these corrections and see what they give in each particular case, and either they zero or not, and what do they give, and is it consistent with holography in some cases? Yeah, I think that's an interesting question.
yeah, I think there are corrections that do not depend on a continuous coupling, right? So if you have something that depends, let's say, on the value of the dilatant, then that should not matter. But if you have something that is pretty coefficient.
Yeah, okay. Yeah, that's for sure. Okay, and the last two comments are, well, another point that we try to make in that paper with Luke and Murat is that you can also ask about non-perturbative contributions like wormholes and other things to the index. So we know that if we put several boundaries and compute the partition function, then contributions that connect different boundaries are related to ensemble average of quantum mechanical system. And basically the argument is that because all these wormhole contributions are non-supersymmetric, they should all vanish because of fermion zero modes, similar to the case of n different from zero that I mentioned before. So in this sense, supersymmetry protected quantity should be insensitive to the factorization problem in this particular sense. And another question that maybe probably I should finish, but is that there are also non-perturbative contributions that correspond to pulling defects. So replacing the ADS2 by a defect at the horizon, and the defect can be made smooth by adding certain gauge fields and rotation. And summing over those defects, there are examples where they are important to get an integer for the index. So that's another direction we are exploring, that one can try to understand those calculations better. And maybe understanding how to do a gravity path integral that gives an integer maybe helps to understand the microstates or something of these black holes. Okay, that's all. Thank you for your attention.
Any further questions for Joaquin? Luca trying to ask a question? Okay. If there are no there are no more questions.
Well, I'll ask a question. So in the multi-center case, do they all have to have the same temperature or how do you?
Yeah, that's.
You might imagine a multi-center where they're all, several near-extremal of different but low temperatures. But is that a consistent geometry or?
Yeah, that's why we thought this was interesting, because if you are not computing the index and you're computing the partition function, then you cannot do it, right?
Yeah.
Because if difference, yeah, then I think you cannot do it. But I think with these ones, you can put them at finite temperature in a consistent way for the supersymmetry case. But that's kind of what we are trying to do with that.
Let's start talking.